you're good.
And Linda's out there because I heard her, but also she has these slides up and things like that. And Linda, I was very terse. In fact, I probably didn't say anything at all. But the reason I packaged that way is we might end up going back to part one, time permitting, or not. Okay. So anyway,
Okay.
and I can advance the slide. Well, actually, these are slides, I guess. Yes, they are. Okay. So I'm advancing the slide. Now I'm going to talk. Yeah, there was a question, Linda. You probably saw it.
You want me to send it out now?
Yeah, it was about, are they going to get these things sent to the emails or to their via email? And I'm sure the answer to that is yes. The easiest way for Linda to do it, though, is probably not, it's the easiest way for me to do it too, is not to do it in real time here, because that means shutting down Blackboard and, or not shutting down Blackboard, but going to a different place. And so I have no idea, Linda. I would probably, you probably can't do that in parallel, I don't imagine, right?
No, I can. I'm doing it right now.
Oh, all right, excellent. Okay, so the answer to that then is yes. All right, now back to whatever I was going to say. Oh, yes. Okay, now tonight's big thing, I suppose, is that the review continues, and I'll say more about that later. But I am going to, I was anyway, going to let Linda talk first. And Linda, of course, is a young woman, and that means that she probably can do like 10 things at a time. But anyway, she was telling me about a new process that she thought would work better, and I know she's thought about that. So, Linda, do you want to talk about that, or do you want me to buy you some time until?
No, I'm good. So I was thinking for the review session, then instead of just having, yes, I'm done, no, I'm not done, then what we'll do is we'll give you guys like 5 minutes to try the problem, because it seems like a lot of people don't quite know where to start with it. So 5 minutes to try it on your own, and then I'm going to include an option asking for more time. So if you guys do feel like you're getting the hang of it, you just need more time to work on it, then that's fine, and you can pick that option.
Okay, and Linda's comments are welcome at any time. Linda, just another thing while you have the floor now, though. Last time you asked about GSG things, and maybe that's all been covered, but is there any updates for that for anyone here?
No updates, just the same as what we decided last time. So there will be a GSG on Tuesday before the final at 5.
Okay.
And that's using the same link as always.
All right, excellent.
Okay. I did have a quick question. Someone came to the GSG earlier, and they're wondering if we could bump it from 15 minutes to submit the PDF to 30.
I don't care. 15 really should be enough, but actually, that's up to me. That really doesn't have anything to do with the folks. So yeah, we can do that. So we'll let it be 30 minutes then. I'm not sure I understand that, but I don't have to. It's just that's a request, so I'm okay with that.
Okay.
All right. Anything else, Linda, or is that it?
Nope, that is all.
Okay, and Linda probably has those things en route to you now via email.
Yep.
And I don't know
everything has been sent.
I don't know if you used the Quickly thing or not, but you could have sent it to both classes at once, but I don't know if you did that or not. And that's okay. All right. Now I am talking. So that is the gym part of this. Okay. So I'm reminding you all that there is a mandatory final exam on Tuesday. Now, mandatory means that it's required. If you say, "Oh, I'm just not going to take that," well, that would be devastating to your grade. So you don't want to do that. It is a mandatory final exam, and Linda and I are tonight and the other day, and much of what we've done along the way, is to prepare you for this. It's only going to be about physics. But one thing I really, really, really am going to encourage you all is have your head screwed on as well as you can when you go in there, okay? So don't go in there being terrified. Go in there, do your best, and that's what you want to do. So where your head is very important. So get your head right as much as you can. We are accommodating all students, but things change at the final exam because, somebody says, oh, I missed the midterm. And, I say, well, that was 2 weeks ago. But you see, the midterm could have that kind of casual thing. This can't, okay? So if you got any accommodations, and I've been, forwarding those to the accommodation folks, and they're working on it. But we are making accommodations, but these accommodations are made before, not afterwards, okay? And so I'm really wanting you to do that. And the reason being, not trying to be mean, it's just there is no after. These things will be graded, and then the College of DuPage has an aggressive schedule for turning grades in, and so accommodations as soon as possible. And then I have to work with the testing folks and so on and so forth. There's a little bit of tweaking going on, and I guess Linda tweaked a little bit earlier when she was saying that someone asked about having a half an hour rather than 15 minutes. That's easily done, and if I had known about that before, I might have put that in this little tweaking thing. I was working with some students during my office hours, and the students were suggesting that, well, okay, so you've got grace notes you're giving us, and you're letting us print out the grace notes, but they really wanted to print out the grace notes before, and then they wanted to go through and, I don't know, put little post-it notes or things like that. And after that discussion happened, I'm going to be very accommodating here too. Now, the grace notes are what you get. And if you want to annotate the grace notes, that I guess can happen. But it's going to be what I'm going to tell the proctors, and I'm talking with our proctor tomorrow for this class. In fact, she's wanted to talk to me for a long time, but I kind of was putting her off, not to be mean, but just I thought I'd have better things to say. So I'm going to tell her there is one sheet of paper that you can write on both sides if you want to write some things there to say, oh, that will help me have time, okay? So that's a little bit of a change. You will be allowed one sheet on both sides, okay? Also, when I was interacting with students in my office hours, some of them said that there should be more about trig in there. I don't know if that's the case, but I'm thinking about that, and I'm not opposed to adding it, but I think there was some things in there. And so if it's important for us to write what the cosine is, then we can do that. So there might be a little tweaking of the grace notes, but it's not big tweaking. It's just tweaking like this. You will be allowed to use Excel. You will be allowed to use the PC calculator. But then this is really important. The answer sheet in Blackboard will be the primary assessment instrument. And I know some students say, oh, gee, I struggle with that. I really didn't know how to do that and things like that. I really want you to do that because that's where I'm going to look. And if there's not an answer there, that meant, oh, gee, I really didn't do that problem. Okay, so that is the primary grading thing. And the thing that you're faxing in, I guess I gave you now a half an hour, is it will be a secondary backup kind of thing. Okay, so can we practice using the calculator? There might be one problem tonight when first of all, I would say certainly you can practice, and we might have one problem later on tonight where Linda may end up doing a calculator thing. I don't know. Um, if you have a Mac, and by the way, I used to use Macs all the time when I worked in industry. I don't use Macs anymore for a whole bunch of reasons. That's a long story. Uh, I, if you just use whatever is on your the thing that I would call a PC, okay, it's a personal computer anyway. So I don't have a problem with that. And should I use the Google one? Just you're not coming in using a programmable PC, I guess, or a programmable thing. I'm trying to have a level playing field, okay? So, and certainly you can use Excel because I told you could use Excel, and that's one of the reasons we practice. Okay, and Linda talked to you about Excel. Linda talked to you about how you can do that. So anyway, this is not going to be a problem, okay? It'll be permissive, okay? All right. Wow, Linda, that took way longer than I expected it to. Let's do I'm throwing this off open for Q&A, and so I guess people have been writing questions up there on this. And I think I've answered most of these.
As long as it's a clean copy, it should be fine.
Yeah.
So we can't write on our grace notes, but we do get a piece of paper that we can write on front and back.
That's beforehand. Like, here's what would be a perfect thing for someone studying, I think. You study the grace notes and you say, yes, I will have those grace notes. And then I maybe say, oh, and I think there's 4 formulas that I really need and I don't want to spend time looking for them. So I want to put them on my little piece of paper. And so, then I'm letting you do that. And Linda, someone asked along the way if the new grace notes will happen, and I'll probably try to do that. But there's actually not going to be much change at all here. Okay. All right. And then what we're going to do is we're going to do some review. Now, what I did before this class, and it was based on what happened last time, and was also based on people that came to my office hours, some question that they asked, and also I'm going to be doing this in real time. So I've decided an order that we're going to do things. And so as we go through this, I can be flexible, but I think this is going to serve you well when we go through this. So we do have an order here. And what will happen is if we finish all these things, we might not, but if we finish all those things, we'll jump back because actually students found value in some of those other things in the review that we didn't get to. Okay, so now I'm throwing this up for the question and answer, and then Linda, after that, we'll do, I know we had some questions and answers here, but I'm throwing it off for anybody else that wants to ask a question, and maybe there's somebody who asked a question I didn't answer yet. So do we have anything else from students? Okay. And again, students can always ask questions, and Linda, you can always say things. Linda, let's do a wellness poll and see how people are.
So Professor Bradley, I have a question for people. On this Grace Notes summary sheet that they're allowed to have front and back, can they put down practice problems? Like examples for them to reference during the test?
I don't think that's going to fit on one page. Do you, Linda?
I mean, depends how small they write, but...
You can put it, I'm not going to police that. You can put whatever you want there, but that's what you really want to, yes, Linda, they think you're funny too. Okay, a lot of my students think Linda is funny. I mean funny in a good way. Okay, what happened with that? So we had some people who were struggling. You know how to fix that, at least relative to this class. Jessica's hand's up. I will call on her.
Okay, so I just want to clarify. We can't have all 35 sheets. We can only have one grace note?
No.
Okay.
No. You get to, I guess I'm going to say you get to have 36 sheets.
Okay. Okay. I see what you're saying.
The 35 grace note sheets, but then, I mean, this came up in a thing, and again, I am not your enemy. I am your instructor, and so anyway, Jessica, I would say you can have 36 sheets. I'm just going to tell them, hey, and if they have one sheet, that's okay. But going back to Linda's, well, I don't know if it's Linda's comment or on behalf of people or something like that. One time I gave, and I don't do this anymore, but it was in a classroom, but I gave a open book test. And this one guy thought he didn't. There's not going to be many differences between these two. In fact, tell you what, you get the one sheet, it'll be the same grace notes. I'm changing this in real time. Okay, so we're crossing that out. There's no new grace notes. You'll get 36 sheets. You've got the grace notes that you have, and then you can write whatever you want on that one sheet of paper. And I was going to tell you a story, but I think we need to be moving on, so no stories. And so if you're struggling, you know how to fix that. Okay, Linda, I'm advancing the slide, and here we go.
Okay.
All right. Now, we already have talked about refraction taking place at the surface due to different velocities and also indices of refraction. So things happen there. Linda, if you can go to that website that's a grace note there, and where it says restart, we'll actually look at what happens there, and then we'll come back to this slide.
Yes. Give me one moment because I have to get that up separately.
Okay. So Linda's going to show that. I will continue reading while she's doing that, though. And down here, and I'm grabbing my pencil. Linda, you tell me before you change it, and then we'll be ready and we'll be synchronized. Okay.
I'm ready to do it anytime you're ready.
Okay. But this is the formula I already gave you, but that's the important formula. Dimpy has some comment. Is this about what we're talking about, or is this about something totally different, Dimpy?
It's about the thing that Linda told us, that can we have practice questions on a hand on an exam day?
Yes, but it may not be the most efficient use of space on your paper.
Like the one which are practicing right now, can we have that thing in a copy on that day?
No, you can't. You have one sheet of paper and the 35 grace notes. And if you have anything else, there will be a testing irregularity form filed on you. Okay. And
Okay,
so
no problem.
you can have 36 things, and you can put anything you want on your piece of paper. In fact, some of you, have pictures of smiley faces or crying faces or things like that. You can have all those on there too. Okay, so that's all good.
Okay, no problem. Thank you.
Okay, so now back to course material. This is the equation I showed you last time, but this is different because you see this has the velocities, not that. And you might say, well, Jim, why are you talking about that again? Well, if I were a student paying attention to this, what I'd say is, gee, he went over that again. Maybe I really need to know this. Maybe I want to put this equation on my special sheet of paper instead of hunting for the grace notes for it. But anyway, that's what Snell's law is. And we're going to look at this picture in just a moment, but Linda's going to show you actually a demonstration of this. So Linda, you can switch it now. Thank you.
Okay. There we go.
So she's going to scroll up and then she's going to hit the start. Now this shows you what really is happening. And Linda, just keep doing a little bit on and off, if you will. Just keep going.
Okay.
So you see what's happening there is, you might say, well, why are you drawing a wave that way? Because it's a longitudinal wave, and that's coming out of a transducer, and it's hitting this surface. but you see it is bent. So refraction really does happen. And if you look at the distance between each one of those waves, when you're out in the air between the transducer and the surface, they're closer together. But when they go out, they're further apart. That means it's going faster down there. Okay? And so that's what's happened, and that's what this equation over here is saying. Okay, so Linda, let's just go back to the slide then. So that's the equation that we need. And now you've seen a demonstration of that, so I think that's good. And so there we are, and now we'll look at a problem. So now I'm going to ask everybody, I'm going to read it, and then I'm going to ask everybody to give this a try. Linda will be counting, and she'll be putting up a new thing. But this says, problem 1 says, light travels from air into an optical fiber. It could be something, but they're saying optical fiber. And the index of refraction is 1.44. In what direction does it bend? Now this is using the old equation. If the angle of incidence on the end of the fiber is 22 degrees, what is the angle of refraction inside the fiber? And sketch the path. Okay, so this is the problem. Linda's giving you 5 minutes to work through this and give it a go, and then we'll work through it. You're timing this, right, Linda?
Yep, they got about 2 more minutes.
Wow. Okay.
All right, that is 5 minutes.
Okay. And someone is done, so that is good. And if we were in a classroom, we might ask you to, tell us what you got. But Linda, let's. I'm going to get rid of this on my screen, and then I'm going to advance the slide and try to find the problem. Okay. Yes. Okay. So this is the fiber optic thing here, and you're entering this. I guess I should stop up here. Since the air is traveling from a rarer region, lower in, now this is the index of refraction, that's not the velocity, to a denser region, higher in. That means air is lighter or less dense than the glass in the fiber, okay? And so it's moving from a lower in to a higher in, so it will bend toward the normal. And you see this isn't too dramatic here, but it does bend closer to the normal. Okay, so we have that. Now question B said, what is the angle? And this is more the kind of question that Jim would ask. What is the angle? Well, here is, I guess I do have my pencil. Here is, maybe I don't. Yeah, here is the law. And the law meaning this is Snell's law. And so this is 1 times the sine of 22 degrees is equal to the index of refraction here times the sine of theta 2. Now, please understand that if you're dealing with a problem that has an index of refraction, Snell's law is stated. It's not stated differently. This is the one that deals with the index of refraction. If it's dealing with velocities, it's that other equation that I showed you. But you see now, you can use your calculator to figure out what the sine of 22 is. And apparently, so we figure out what the sine of 22 is, and we divide both sides by 144, and we get that the sine of theta 2 is equal to this. So that means to do this, then you would use your calculator, and you would say theta 2 is equal to the inverse sine of 0.260. This is very much the kind of problem that I might ask you about angles. The one came from the fact that in air, it was in the statement of the problem, okay? But air out here has an index of refraction of 1. I think the problem said that. And don't be sorry, you're asking a good content question. That's fine, okay? So that's good. Linda, anything else we should say about this, or do you think this stands by itself now?
I think that covers it.
Okay, remember, it's bent to the normal. Now, Linda, I'm going to go back and we're going to look at the other. Maybe we'll look at this. I don't know, or maybe I'll leave it for students to do. Let's see. Oh, okay, this is a little bit different. Linda, let's don't give them as much time on this, though. And we're not going to do B. We're just going to do A. But everybody do A. for this, and so I will read it. Light traveling through an optical fiber. Now it's in the fiber, it reaches the end of the fiber, and it exits into the air. It's going the other way. If the angle of incidence on the end of the fiber is 30 degrees, what is the angle of refraction outside the fiber into the air? So you want to work on that just for a moment, and that'll give you a chance to practice using your calculator and doing it, and you should benefit from sample problem 1.
Well, they've had a few minutes and the only answer was no until 1 second ago. So,
Okay, so I'm going to close this out, and we'll look at a solution to this. Now, so the solution is not that one. That's the one we just looked at. It's this one. Okay, so it's going in the another direction. So this is the equation that you're writing. So you see you're trying to figure out what theta 2 is here. And you should have got for this one that theta 2 is equal to 46 degrees. And again, this is something that you can practice. And we did talk a little bit about critical angles, but I'm not asking you that on the test. I will say that. But now we're going to go to another problem. And here's a drawing. And I want you to think about this drawing. Now here, this is the boundary, the up and down thing. And I think this is kind of the way I draw the picture. Actually, I'm not sure. No, actually, I'm lying. The boundary is here. This is the boundary. So you got an incident ray coming in here, or a sound wave, and some of it is reflected, as we talked about, but also some of it is transmitted and refracted. And this actually is very much like the problem I'm asking you on the test. So suppose the ratio of, but this is not the ratio of N1 and N2. This is the ratio of V1 and V2. So it's V1 over V2 is 1 to 3. And I tell you the measure of angle theta 1 is 5 degrees. What is the measure of the other two angles? And so Linda's clock has started. We're doing this one. This is very much like the problem I think I asked.
So you guys may not be finished, but can you hit yes if you feel like you've got a good start and know what you're doing?
We may continue to refine this methodology, Linda.
Yeah, basically.
If we do it again. And by the way, I think I'm slated to do it again, and I would love to have you along with me if that could happen. So anyway,
Sounds like a plan.
We could try that later, but anyway. Are we about there?
Yeah, they've had about 4 minutes, and that
Okay.
seems like all the responses we're gonna get.
Okay, so I'm doing that. Now, I want to go back and say something that's really quick. The angle of incidence is always equal to the angle of reflection. So you see theta 1 has to be the same as theta 3, and that would be partial credit on something like this. So the angle of incidence is always the same as the angle of reflection. But the other thing, the relation between, so if this one was 5 degrees, then this one over here is also 5 degrees. But the relationship between this guy, theta 1, and theta 2 is different, and it's defined by Snell's law. So I'm going up and trying to find that. Okay, so the equation then that we're looking at here is, and I still have my pencil, so that is good. So this is, and this is the one I had before. So we're looking at sine of theta 1 times V1, no, times V2. Actually, I should do it the other way. I don't have an eraser that I can do, so I'm just going to do it this way. The sine of theta 1 over the sine of theta 2. And this is different for the velocity than it is for the index of refraction, is equal to V1 over V2. And I think I told you that V1 over V2 was 1 to 3. So this is 1/3. And I also said, I think it was theta 1, this really was 5 degrees. So I really have a number there. Okay. So the sine of 5 degrees is this. And so that means what we're doing is we're talking about the sine of theta 2. I got to start using my touch sensitive thing. The sine of theta 2 then is going to be 3. You see I'm cross multiplying times that. So this is going to be 2625. And so that means that theta 2 is the inverse sine of that. And that is going to be that in degrees. Now I am going to pause just for a moment on this one for questions, because actually this is pretty similar to the problem I asked. Not exactly, but it's pretty similar. Yeah, Sydney.
So basically you're cross multiplying the number that's
Yes.
the sine of 5 degrees with 1/3.
1/3 times the sine of 5 degrees, right?
Okay, to
If I
figure
take,
out.
so I'm taking 3 times the sine of 5 degrees. So here's what the sine of 5 degrees was. So 3 times that is this guy.
Okay.
And that's equal to the sine of theta 2.
Okay. Thank you.
Somebody had their, somebody said a comment, but the comment went away. So I'm not sure. Linda, did you see the comment?
Yeah, it was just a notation thing, but I'm pretty sure that both notations mean the exact same thing. So,
Well, if you want to say more to answer the question, I really didn't see the question. I didn't catch it.
If you go under the chat, then you can see all of them.
Okay. So that's not up here. Where is that?
So on the bottom right-hand corner, if you see two little arrows sticking out that are
I got
purple,
two little arrows
so
there.
hit that, and then on the bottom on the left, then there's a little chat bubble, and it tells you
Okay.
how many messages
All right,
to read.
so here is the, somebody just said it was 15 degrees. If you keep going to the decimal points, you get that, and I will give you guidance as how you should round that, okay? So you want to use as much information as you had, and actually the closer answer is 15.22, okay, if you're rounding it that far, okay? All right, so, and I don't know, let's see, yes, I will give you guidance about rounding on each problem. I'll tell you how you should round your answers. Okay, so this is a good one for you to make sure you understand, and that's why I spent so much time on it, I think. Okay, let's go into something else. Now this is the problem that was your LSA, and I've totally lost track of what this number was.
This was the last one, so this was 17.
It was the last one, whatever that was. So a 2 megahertz sound wave travels through a pregnant woman's abdomen and is reflected from the fetal heart of her unborn baby. So the heart wall is moving towards the sound receiver. By the way, I'm talking about Doppler because there's a Doppler question on there. The reflected sound is then mixed with the transmitted sound, and 85 beats per second are detected. The speed of sound in body tissue is this. That's the number that I guess we'll look at in the solution. And we'll calculate the speed of the fetal heart wall at the instant this measurement is made. Now you were supposed to have worked on this, and so I'm okay going to a solution. And this is the solution. Now, if you're looking at this, I bet you're saying, oh my gosh, that's really, really complicated. But this is using the very general equation for the Doppler shift. But I gave you a different equation. And Linda, and I know I'm hitting you cold with this a little bit, but what I'd really like for you to do is use the ultrasound equation. And Linda, I'm going to dictate that to you if I may. So
you want me to write it?
Yeah, you're writing, and you're going to, I think, solve this for us. And so yes, please write it. So it's going to be Doppler shift, or just say shift equals, and then the numerator is 2, and then it is times the transducer frequency. Times cosine of theta times V, all divided by, and that's the propagation of sound, but it's going to be 1500 inside tissue. Let's try 1500. Okay, now Linda, now the 2 is there because I told you the 2 is there, and the angle theta is 0 here, but in the test I might have you doing something else with that angle. But what Linda's going to do is she's going to put some numbers in here, and she's going to solve for V. So Linda, the shift I think was, let me go back and find out so we really know what the shift was.
I believe that was 85.
The shift was 85. You're right, plus 85.
Okay.
Is plus 85. And the, did I erase that on you? Damn it.
You did.
Okay. I'm sorry, I didn't intend to do that. Okay, and it was at 2 megahertz, so it's 2 times 10 to the 6. Cosine of 0 degrees is 1. So it just kind of isn't cosine of 0, but that's going to be 1.
That's
and
just
then,
a 0, not a theta.
That's going to be 1. times V, and that's divided by 1500. So you see, you just got to solve for V. So Linda, can you take us through just solving for V? And if you need to use a calculator, that's fine. But we're going to get an answer, and we're going to see that this was pretty much easier. Go ahead.
Okay, so first thing I'm doing is multiplying both sides by that 1500. So that'll give me 85 times 1500 over here. And then just to simplify things a little bit for myself, then 2 times 2 is 4. So that's 4 times 10 to the 6th. Cosine of 0 is just 1. So I just have my V left. So then I'm going to divide both sides by that 4 times 10 to the 6th. And then just throw all that into a calculator. So
And
85.
go ahead and tell us what you get when you, or actually everybody out there, you have your MacBooks or PCs or whatever that you're watching this on. So go ahead and do that calculation, and we'll compare notes with Linda's answer for V.
So I'm getting 0.032.
Okay, go ahead and write that down if you will, Linda. Now, it's really important though, Linda, what units? Yes. Okay. And now I'm just going to go back, and by the way, Linda's answer is right. And it's right if you put those units on it, but watch what these guys did. First of all, these guys rounded a little bit differently than Linda did, but that's okay. But they had centimeters per second. Those are the same answers, yes. Here was their meters per second. Is it always going to be 10 to the 6th?
If it's megahertz, yes.
That's right. If it's not megahertz, it's not. Okay, now that's good. Now, I had Linda do that because I wanted you to realize that, wow, this is like really complicated. What Linda did was much easier. I'm asking you a question that's like that, although theta might not be 0. You see, so far, and even though this review, you might say, hey, we're not going very fast. If you understood both things that we did tonight, you've got 2 of the 10 problems correct already. Okay?
2 of the 11.
I'm sorry?
There's 11 problems.
2 of the 11 problems. But that's 22%. So we already did that. And here's some more Doppler problems you could practice if you wanted to. And here are the solutions to those. Okay? But now we're moving on to something else. And this P and P stands for pressure and Pascal's principle. And again, I've done triage on this stuff. So if I'm talking about something, it's meaningful for you to understand. In fact, I wish you understood everything we talked about in the course, but this is the day before the exam, so I'm going to read this. Okay, suppose the hydraulic lift shown in the picture, here's the hydraulic lift down here, has a small cylinder piston with a radius of 5 centimeters, that's the one over here, and a larger piston with radius 20 centimeters on the other side. The mass of the car placed on a larger piston is 1,000 kilograms. Assume they're at the same height. What force must be applied to the small one to lift the car? And then it also says, how far must the small piston move down to lift the car? This far. Okay, give it a go. We'll look at a solution whenever Linda says it's time to look at a solution.
All right, it's been a few minutes, and so far we got one no, so I'm gonna call it.
Okay, so we will look at the solution to this then. All right. Okay, now the main equation here is that the force 1 over the area 1 in a hydraulic system like this is the force 2 over the area 2. Okay, and that's actually the same thing as this equation, because this is just a thing if we would cross multiply Sydney like you were talking about before. That equation I circled was that. Okay, but then you got the area. Now they told you let's see, they told you the diameters, I think, or maybe they told you the radius. Actually, it didn't matter because the ratio of the squares would be the same. So you plug in numbers and you get this. So the force of this can lift a car weighing that much. Okay, and so down here then, if the small piston moves a distance of d1, the volume of fluid displaced is this. And because the total volume of fluid is constant, V1 must equal to the volume of V2. And so it follows that these two things are equal. And so if you solve those, you find out that that the answer this for D1, you must move 1.6 meters for the small piston to move this one. So it moves further, but it's less force. And that's the advantage, that's the trade-off that happens here. Okay, so again, this is a key question. There are examples in your book of this. And in fact, here are two more.
That's pretty dang close.
Yeah, that's going to be close enough. I'm sensing that maybe, actually the pi's canceled, so I'm not really sure what they did. I'm not sure what the student did differently, but that would be close enough. That is close. That's fine. And let's just go with Linda's comment on that. Hey, there's some other problems about pressure that you could try to practice, and I give you solutions to those. Now this one, okay, so what have we talked about so far? We've talked about pressure. We've talked about Doppler. We've talked about Snell. That's 3 of the 11 problems. And we talked about some others last time. I'm talking about conservation of energy, and I say I'm talking about conservation of energy again. Now there's a reason that I'm doing it again, and I guess that's underscoring it definitely is there, but this is different. I will read it. A slingshot obeying Hooke's law is used to launch pebbles vertically into the air. You observe that if you pull a pebble back 20 centimeters against the elastic band, the pebble goes 6 meters high. Assuming the air drag is negligible, how high will the pebble go if you pull it back 40 centimeters instead? And B, how far must you pull it back so it will reach 12 meters? And if you pull a pebble that is twice as heavy, how far will it go? So this is about conservation of energy. And Linda's starting her clock. And Linda, it's about 6:58 or so.
Okay, we'll give it a couple minutes.
All right.
Well, at least one person is done, so I'm gonna call it
Okay,
just so we can get through more.
let's go. And again, Linda is actually being prudent with the time. Now, why did I ask you this question? Well, you see, this is different because we did gravitational potential energy before, and gravitational potential energy certainly can change into kinetic energy. But this is not gravitational potential energy. This is elastic potential energy. Elastic potential energy that is being changed into kinetic energy. Actually, I don't think I should have really put an equal sign there. I should have put like an arrow going both ways. But you see that changes, so that's what's happening. And I could ask you both, and given that I talked about this one, you might think, oh, that's what we're doing. And you see here is pretty much the equation that we talked about. This is the, in fact, what happens here is you're using the potential energy, the elastic potential energy to shoot it into the air. And I think the question was asking how high did it go? Yeah, how high did it go? Well, look, this elastic potential energy is changed totally into potential energy. And so what you can do is you can set those two things equal, and we're solving for H, and we get that H has to be 24. And they do some cute things here, but you can do that without doing this fancy proportional kind of stuff. And then you can solve to find out what is, trying to remember what the second question was for B. Oh, how far must you pull it back? That's the reverse of that question. And you have to pull it back this far to get that height. And last but not least, they're saying if you make the pebble twice as heavy and you pull it back, how far will it go? And you see that, let's see, let's go find that one. I think I went the wrong way. There we go. Okay, and you see that it's going to be 3 meters. Okay, so this is a different kind of conservation of energy, and that's why I talked about that again. Okay, a range equation. Now, the range equation, and Linda, we are going to have them give answers for this one, okay? But the range equation, this is purely a ultrasound question. It is based on physics, but it says the range equation, the go-return time in an ultrasound exam is 65 microseconds. How deep was the reflector? And Linda, we don't have to give too much time here because this is a pretty quick question.
So how are they submitting their answers? Just in the chat?
On the answer sheet. I mean, I'm sorry, Linda, I'm not understanding your question, I think.
So they're answering it now, right?
They should be answering it right now.
Okay, so.
And I mean, they're not submitting them. I'm just, okay, everybody should have an answer already. And
okay.
This is 5 centimeters. Okay, and this is called the 13 microsecond rule, isn't it, Linda?
Yes.
Okay, and by the way, be careful though, you got to read the problem because I said the go return time. I could mix that up and I could have asked you well, I did ask you how deep was the reflector, but I could have given you different things and I could have said, how long did it take? Or I could have given you different kinds of things. So what you should do is go study the range equation. We went over that in a VCM class, and it's in the notes. Yes, Sydney.
Is the depth always measured in centimeters?
Here's what the 13 microsecond rule says. For every centimeter of depth, The go return time is 13 microseconds. I thought that was an answer to your question. Maybe it wasn't. I think it was.
It was.
Okay.
It answered it. Sorry.
All right. So look, now we're up to 4. That's almost 40% of the test that we've covered tonight. Okay, and we're not finished yet, but I am watching time, so don't worry about that. Now here's another one, and this is about velocity, wavelengths, and frequencies. Now there's a lot of things to check here, and you might say, well, Jim, why are you talking about this tonight? Well, this is the night before the test, so this probably has something to do with it. Let's just talk about one of these things, and there's a whole bunch of examples here. Let's talk about number A, I guess, whale communication. Whales communicate using a frequency of 17 hertz. By the way, that's a low frequency. That's not kilohertz or megahertz. That's hertz, which can be heard 1,000 kilometers away, though. So it goes a long way. So if whales were trying to find other whales, they could talk over big distances, I guess. What is the wavelength of such a sound in seawater where the speed of sound is 1531 meters per second? Well, and in the interest of time, because it's about 7 after, we're just going to go here. But the real reason I wanted to talk about this problem was that's one of our fundamental equations, isn't it? The velocity of the wave is frequency times the wavelength. And an easy way to remember this formula, I know you don't have to memorize it, but an easy way to remember this formula is this comes in meters per second, and frequency is going to be reciprocal seconds, and this is going to be in meters. So you see the wavelength, and these are very long wavelengths, but the wavelength of this whale's call to other whales has a wavelength of 90 meters long. And if you look at this, you say, wow, and all of these just mess around with different versions of the same equation. So, Linda, I don't know, this might be something you put on your short sheet.
Yeah, I'd say so.
Yeah, okay, let's see what else. Density. Density actually is dealt with in the test, but it's kind of in the middle of the problem, so you can practice it here, but I'm not going to talk about here. Vectors, we talked about vectors last time, so that's good. There's some more vector problems that you can practice. Linda, if we can, what I'd like to go back, and let's go back to the earlier list. And Linda, that was the thing from last time. You know what I'm saying?
Yep, I gotcha.
All right, and go try to find the dimensional analysis page. And you see what we've done is we had about 5. Here we go. Okay, great. Let's go back to that. Okay. There is a dimensional analysis problem, and I'm trying to think of what it actually, I'm remembering what it is. But let's just talk about this one up here. Okay. So we're driving in an exotic foreign land. You see a speed limit that says 18,000 furlongs per fortnight. You might say, well, what does that mean? But you're supposed to change that to miles per hour. This is what dimensional analysis is called. Now, you do have to be given information. A furlong is 1/8 of a mile. It is a farming term originally, but it really had to do with horse racing more recently. They talk about races being, there are 8 furlongs per mile, and that's how they talk about the length of horse races often. And a fortnight is a unit of time. So you see this is distance over time. So it is a velocity, but you have to change that to miles per hour. Now, Linda, let's give them maybe a couple of minutes to try to write out the equation. Maybe they won't do the calculation, but maybe they will. So everybody give this a go, and then we'll look at a solution. And Linda, this gets us up to 5 of the 11 problems, right?
Yeah, I think so.
Tonight. Okay, planning helps, I think, sometimes. Okay, everybody, you got a couple of minutes, and then we'll look at a solution to this. Okay, Linda, I'm probably going to just call it. Okay,
Okay.
so let's go and look at a solution. And that's not our problem. Am I on the right page? Yeah, I think I am.
There we go.
Okay, good. All right. So the big thing is you set this up and you see we want to have miles per hour as our units here. So we start out with furlongs per fortnight. This guy cancels with that guy because this is in the numerator and that's in the denominator. And this is my conversion factor. This is really multiplying by 1. So 1/8 is 0.125 miles. That is 1/8. At this stage of the game, we have miles per fortnight. But then we multiply by fortnight per days. So the fortnights cancel, and now we have miles per day. But then we multiply by hours per day, and the days cancel, and now we have miles per hour. Now you do have to multiply this all the way across. That's very easy with Excel, but you would get 67 miles per hour. Here's another problem that you certainly could practice on, but there is a dimensional analysis problem that is there. Linda, we probably don't have time to fully do another problem, but I'm going to go up here and just point to another thing that certainly we have. We have rectilinear motion problems, and so there's 2 there, and the solutions, and that's another good one. And I guess I'm maybe going to claim we've talked about 6 out of 12. We talked about some other things last time, so I think that's pretty good. Linda, let's do 2 polls if we can, Linda.
Okay.
Okay. First poll is going to be, does mindset matter, yes or no? I want everybody to respond to this. Does mindset matter, yes or no? Well, the answer is yes, mindset does matter. Linda, the last poll of this class is going to be, should your mindset be positive or negative? That's right. It should be a positive mindset. It'll make a big difference. Prepare well. Go in there and do your best. And that's all anybody can expect of you. That's all you can expect of yourself. So get her done. Anything else, Linda?
No, I think that covers it. You guys have
All
done
right,
great.
So Linda will probably upload, or let me ask it this way. Linda, is your life such that you can get that done?
Yes, I can do that immediately after the class ends.
All right, excellent. So, okay. And by the way, accommodations, get them done. All right. Okay, we're done, and I'm going to turn off the recording.
Have a nice night. Thank you.